This conference will now be recorded.
Uh, we are discussing about convolutional codes. Convolutional code. And in the last classes, we are discussing in detail about its encoding. And later, we have seen that Viterbi algorithm, which is used for that, it's a decoding. And here, a convolutional encoder is given. And we have seen how we can give the dimension of this convolutional code. Can anyone say what is the in two ways we have represented? One is in terms of that as code rate and constraint length, that is in terms of that code rate and constraint length. Therefore here we can write the code rate here as code rate is nothing but k by n. Here k is equal to 1 here, that is corresponding to each message bit we are generating two outputs here, v1 v2, two output. There are two adder elements here, therefore 1 by 2 is its code rate. And constraint length here, it is 4. It is k equal to 4, k or capital L, it is equal to 4. Sometimes it is given as capital L. It is the one method of representing its dimension, that is code rate and constraint length. Here code rate is 1 by 2 and the constraint length is equal to 4. And another in another way we can write the dimension of this code as 2 1 3, a 2 1 3 convolutional code. Okay, this we have discussed in the last class. 2 1 3. 2 1 3 is the dimension of this code. And here later we have seen that generator sequences representing it. From that we are that is we can represent it as that generator sequences G1 and G2. G1 and G2 are the generator sequences representing these two adder elements, one here and one here. And the elements we can write as G1 1, G2 1, G3 1, G4 1, and the here G1 2, G2 2, G3 2, G4 2. These are the in general the generator sequence. In this particular case we can write this G1 and G2 as, can anyone say these two sequences? We can write in the chat box G1. What is G1 here? What is G2 here? From this connection to this adder elements, we can write the generator sequences of these adder elements. Please someone write in the chat box the answer to this. What is the G1 and G2 here? No response. I'm audible, isn't it? Please respond yes or no. Someone please.
Yes, sir, audible.
Okay. Okay, here we have the first adder element, that output v1 is equal to, we have m XOR. It is not connected to this m1, therefore m that is here we can write this v1 is equal to m XOR m2 XOR m3. Therefore we can write the generating sequence as 1 0 1 1. And similarly for g2, the generating sequence representing the second adder elements, it is connected to all, that is that v2 is equal to, here we have that v2 is equal to m XOR m1 XOR m2 XOR m3. Okay, therefore we have 1 1 1 1. That is the generating sequence, and or generating sequence, or we can say the impulse response of this adder elements. Impulse response, you know what is meant by impulse response of a system. Here the g1 and g2 represent the impulse response of this adder elements, and we can write the generating sequence or impulse response from this connection, that convolution encoder representation. We can write that generating sequence. Then we have seen that that output is equal to this. We have that output, and it is the combination multiplexed version of that v1 and v2. Okay, v1 and v2 we have here, v1 and v2. First output will be v1, then v2, then this switch alternately connected to v1 and v2. Excuse me, anything? I has heard some sound. Okay, v1 and v2, and that is the output. And we have seen that v1 is equal to the u convolution g1, where u is the input sequence. We have u is the input and v is the output. That output v1, first sequence v1 is the convolution sum of input and the impulse response of the first generator sequence, first impulse response of the first adder elements, u convolution g1, and v2 is equal to u convolution g2. This we have discussed in the last class. It is the one method to find the output, that is the time domain approach. Once we can find the output in any way, that convolution sum, then this multiplexed version of v1 and v2, that is the final output v we have, corresponding to this input u. Then we can take an example, that is u is equal to 1 0 1 1 1. I think we have done the same example earlier, and we will have to find the impulse response of this convolution code corresponding to this u. And we have that v1, that sequence equal to impulse convolution sum of the input 1 0 1 1 1 convolution, that g1 we have 1 0 1 1, and v2 is equal to the input sequence 1 0 1 1 1. It is given here. U is 1011. We'll have to find the convolutional code that corresponding to that. Then G2, second impulse response of the second adder elements. Here it is 1 1 1 1, and here the output we have obtained is, you can check, you can make, in the last class we have, I think I have done the same example. Find the convolution sum of these two sequence, that is input and the impulse response of that first adder element. Here the input and the impulse response of the second adder element, and we have obtained the output as 1 0 0 0 0 0 0 1, and second, that V2 sequence is 1 1 0 1 1 1 0 1. It is simply the convolution operation here, and final output we have, it's multiply 1 1. If we represent as two pairs of that output, 1 1 0 1 0 0 0 1 0 1 0 1 0 0 1 1 0 0 1 1. It is the final output. And here this particular output can obtain in another way. That is, here we write the impulse response of the generator impulse response of the adder element, or that generating sequence G1 and G2 like this. That is, here 1 1, that is we write taken 1 1 0 1 1 1 1 1 like that. That is, here I will write 1 1 taking more space, 1 1. That is, here first one is taken from this G1 and G2 1 1. Then next is 0 1. Here it is 0 1. Then next is 1 1 1 1 like that. 1 1 1 1. Then we have the first input here is this 1 here, or here 1, or we have corresponding to that one, we have written that particular generating sequences taken in that way, 1 1 0 1 1 1 1 1. Then next we have 0 is the input bit. Then by shifting two position, we can write by multiplying this, that is 0 0. Here all the elements will be 0 0. Okay, then we have the third input bit 1 here. Therefore, by shifting two more bit position, we write this sequence, that is multiplying these two. In that way, we can say, for here 1 1 0 1 1 1 1 1. The next bit is 1. Then by shifting two more bit position, we can write that multiplying 1 1 0 1 1 1 1 1. Then one more bit here, it is that last bit 1. Then by shifting two more bit position for 1 1 0 1 1 1 1 1. Then adding these, that is we can write 1 1 here, then here 0 0, therefore 0, then 1 plus 0 1 here, 1 1 0 here, then 1 1 1 0 1, therefore here also it is 0. More to addition, 1 1 0 here, 1 1 1, so here it is 1, then 0 1 0 1. Here it is 0, here it is 1, here it is 0, here it is 1, then 1 plus 1 0, 1 plus 1 0, 1 1. Okay, this is the sequence we have obtained. Okay, here we can see it is same as that output here. That is here, this 1 1. Check, compare this 1 1. Then next is 0 1. Next is 0 0. Again 0 1 here, 0 1, 0 1, 0 0 1 1. Okay, it is in this method. In this way, we can write the output. Okay, this we have written that G1 and G2 sequence. First bit from G1, second bit G2. First, and then next bit is first bit of second bit of G1. Then it is here 1 1. If there are three sequences G1, G2, G3, then G1 G1 1, G1 2, G1 3. Then next is G21, G22, G3, sorry, G21, G22, G23. Like that, we write the first row. Then shift 3-bit position. We will have to write that next, depending on the input bit, either it is 1 or 0, we will have to write by shifting 3-bit position. Then by adding this, we will get the output. I think have got how we have calculated. This here I am going to write the we can take it as this convolutional code as also a linear code. Then we are able to write the generator matrix. From this, once we have represented this, we can easily write the generator matrix here. Okay, that is my aim here. Okay, hope that you have got this. Please respond through the chat box, yes or no. Please, I need some response, yes or no. Okay, only John is responding. There are 49, including me. That is means 48 there, but no responses. Okay, thank you for my Devika, Adira, Joanne, Navneet, Khadija. Okay, thank you. Then here next I am going to write the generator matrix corresponding to this convolutional code. Here I can say if u has the length, it is that input length is input sequence length is L. Here I have taken this length of the input sequence, that is here we have that capital L 5 here, that is length of the input sequence 1 0 1 1 1. It is length of the input sequence is capital L. Then we have for the generator matrix, that is generator matrix, I am going to write the generator matrix of the convolutional code here, generator matrix G. This generator matrix has L rows and n into m plus L, n into m plus L columns for the generator matrix. Therefore here in our example we have that here that L is equal to 5, that length of the input sequence I have taken in this example as 5, and n and m, n is equal to 2. That is the number of outputs corresponding to each message. That is here v1 and v1 and v2. Therefore 2. That is here 2 1 3 here. That is here in this sorry. Here it is n k m, small letter m. Here it is m. It is equal to 3. Therefore here L is equal to 5 and m equal to 3 and n equal to 2. Therefore we have 5 rows and 2 into 3 plus 5. Therefore 8 into 2. Therefore 16 columns. Okay. For this example, that is in general we can say if the length of the input sequence is capital L and the generator matrix of the convolutional code has L rows. So here in this example 5 rows and n into m plus L columns. N into m plus L columns. Here n the number of outputs, m the number of that stages in the shift register. Here that we have m, m1, m2, m3. Therefore that in that convention m equal to 3. We have seen that two representation in that m here equal to 3. Therefore here in this example that 5 rows and 16 columns, and we can write the generator matrix of the convolutional code as G11 G12, then G21 G22 G31 G32 G41 G42. Then here the zeros I will say that. Then by shifting 2 bit positions, G1 1 G1 2 G21 G22 G31 G32 G41 G42. Then that is here 2 zeros. Then that elements of that generator sequence or impulse response. Then here 0 0 0 0 again that G11 G12 G21 G22 G31 G32 G41 G42. And here also it is here it is 8 elements, then 8 zeros. All the remaining elements will be zeros. Here again 0 0 0 0 0 0, that particular bit. This in the previous example we have that sequence here, that G1 1 1 0 1 1 1 1. For we can write the generator matrix as G is equal to 1 1 0 1 1 1 1 1. Then here 0 0 1 1 0 1 1 1 1 1 0 0 0 0 1 1 0 1 1 1 1 1. 5 rows and 16 columns. 0 0 0 0 1 1 0 1 1 1 1 1 0 0 0 0 0 0 1 1 0 1 1 1 1 1. And we'll have to write the remaining bits here as zeros. Okay, it is the generator matrix here, and here once we have written this generator matrix, we can find the output uh, using the equation, that is that V is equal to U into G. This U is our input sequence and G is the generator matrix. For by multiplying that input sequence with the generator matrix, we can obtain the output sequence, that is here significance of this generator matrix, that is we can say we can see this convolutional code as a linear code. Therefore we are able to write the generator matrix, and here we have seen how we can write the generator matrix of the convolutional code, that is we have seen here. And once we have written the generator matrix, we are able to find the output by multiplying the input sequence with the generator matrix. Okay, that's about that generator matrix of the convolutional code. And prior to that, we have explained how we can find the output sequence in another way, that is here we have represented as sequences. In general, we can say that V1 is the convolutional sum of that input sequence and the impulse response of the first adder elements, and second output V2 is the convolutional sum of the input sequence and the impulse response of the second sequence U convolution G2, and by multiplexing we can obtain the output sequence. And here we can obtain the output sequence in another way, that is first input bit is written, then that G1 and G2 taken together, multiplexed version of that G1 G2. If there are three adder elements, then G1 G2 G3, 3 bits, and then next bit is 0, therefore all the elements are 0, and it is written 2-bit shifted. If there are G1 G2 G3, we will have to shift 3-bit position. It is we can write this we can find this way. This all from the basic definition of that convolution sum. Okay, only that much. Okay, anyway, we have seen this method for finding the convolutional sum, that is the convolutional code corresponding to a particular input sequence, and later we have seen the generator matrix of a convolutional code. Here if L is the length of the input sequence, then we can say the generator matrix G has L rows and n into m plus L columns. That is here in this example 5 rows and 16 columns. 5 rows and 16 columns, that is written here. That is the generator matrix of that particular convolutional encoder given. And once we have written this, we can verify that output can be obtained as the product of input sequence with the generator matrix V is equal to U into G.